Thank you very much. Thank you very much to organizers for accepting our contribution. I'd like to tell you how my colleague Behrang Nuhi and I apply categorical Galois theory to clarify this very classical differential Galois theory, but also vastly generalize it. So let me start with the classical Picard-Vessiot theory. It discusses Picard-Vessiot extension of differential fields. This is an extension K to L such that the constants of the two fields are equal, and L is obtained by adjoining the solutions to some linear differential equation over K. Inside that field L, there is a Picard-Vessiot ring. This is an integral domain whose fraction field is L, but it's a rather special one. So if you take the tensor product of A with itself over K and then take the constants, you obtain a Hopf algebra over the constant field, and taking the spectrum gives you a linear algebraic group over the constants called the Picard-Vessiot Galois group. And the classical correspondence they establish is between intermediate differential field extension between K and L and closed subgroups of G. So now we come to the categorical formulation of Janelidze. He realized that his categorical Galois theory applies to Picard-Vessiot theory. In categorical Galois theory, you have to set up an adjunction and then work from there. The relevant adjunction here is between the opposite category of delta rings, of differential rings, which we consider as affine differential schemes, and opposite category of rings, which we consider as affine schemes. And the left adjoint functor is the functor of constants, and the right adjoint is the functor where we simply take a ring and give it a trivial zero derivation. Now, Janelidze emphasizes that the Galois object here is not what you might think. It's not the field extension L to K. It's actually this morphism F from spectrum of the Picard-Vessiot ring to the spectrum of the underlying field K. That is morphism of Galois descent in his theory, and the Galois, categorical Galois groupoid of F is the Picard-Vessiot, agrees with the Picard-Vessiot Galois group. The famous self-splitting condition from categorical Galois theory, in this case, simply tells you that this X over Y is a torsor for the group scheme G. And the categorical Galois theory establishes an equivalence of categories between split objects by F. So these are morphisms of affine differential schemes with target Y, which are split by F, and G actions in affine schemes. Now, when I visited Professor Akira Masuoka in Japan last year, he asked me, does categorical Galois theory recover the classical Picard-Vessiot correspondence? And I thought, well, it should. And I thought it should do it through the paper of Carboni, Janelidze, Magid, where they establish a one-to-one correspondence between split quotients of this morphism X over Y and effective subgroups of G. One of the functors establishing the equivalence is this one, which takes a subgroup and gives you the quotient X mod G. Unfortunately, not every closed subgroup of a linear algebraic group is effective. So the answer to Professor Masuoka's question is no, because you only get effective subgroups, and H is effective with respect to the category of affine schemes, if and only if the coset space G mod H has the structure of an affine scheme, But from algebraic geometry, we know that in general, the quotient by a closed subgroup might be quasi-projective. So this leads us to consider more general differential schemes. So it's no longer possible to stay in the affine category. Now, there is a serious obstacle to this, and the obstacle is that if you consider differential schemes, and then take the usual functor where you just add the zero derivation on the scheme, so this functor makes sense. But the left adjoint, the totally defined left adjoint, doesn't exist. And we tried different notions of differential schemes, but with none, it works. So we need to find a very novel way how to overcome this obstacle. Now, let me just tell you what I mean when I say differential scheme for the purpose of this talk. If you take a base ordinary scheme S, then an S differential scheme is simply a scheme with a given derivation of its structure sheaf. And there's a way to think about this as determining a vector field on X. And this brings you closer to maybe the way of thinking of differential geometry. So, you think of vector field, and then maybe think of some leaves along the vector field, and so on. Now, this gives us this category of S differential schemes and the trivial kind of functor that takes a scheme and associates a differential scheme with the trivial vector field. Now, what are we going to do about this potential left adjoint? Well, we noticed something brand new that we didn't see in the literature before. So we defined this a little precategory internal to schemes, which is obtained by infinitesimal augmentations of the base scheme S. So this precategory has object of object S, object of morphism is S epsilon, so we adjoin an infinitesimal where epsilon squared is 0. And then object of composable morphisms is not the, the pullback of S1 with itself, because you would not get the middle epsilon 1, epsilon 2. You would only get epsilon 1 squared, epsilon 2 squared. So this is a genuine precategory and definitely not an internal category. And the key observation is that differential schemes, the category of differential schemes is equivalent to actions of this internal precategory in schemes. And notation-wise, when we have a differential scheme X delta, we're going to denote its associated precategory by blackboard bold X. Now, we can define this somehow key object, which is a categorical scheme of leaves. Intuitively, you should be thinking of this as some sort of a quotient of this differential scheme by the action, infinitesimal action of this vector field. And we simply define it to be the object of connected components of the associated precategory X. So it's a co-equalizer of source-target maps. And of course, co-equalizers in schemes very rarely exist. So this doesn't happen very often. But it turns out that somehow key differential schemes for Galois theory are precisely those where this happens, and even slightly more strongly. Okay, now because we are able to view differential schemes as precategory actions, we can very easily tap into theory of descent, because precategory actions are just generalized descent data to some extent. So we're able to establish some rather novel results about descent in differential algebra, which nobody has done before. So, okay, this descent usually works for some pseudo-functor P or some index data on schemes. This is usually either some specific class of morphisms of schemes with the codomain vibration, or it's maybe quasi-coherent sheaves of schemes, or later we'll work with polarized quasi-projective morphisms, etc. So using some classical index data on the category of schemes, P, we can naturally define a differential analog on differential schemes simply by saying that, on a differential scheme X, we just consider the precategory of actions, precategory X actions with respect to P. So we are able to prove this theorem starting with a morphism of differential schemes. You obtain the corresponding morphism of precategories, and F is effective descent for delta P if F0 is effective descent for P and F1 descent for P. So, this is kind of rather strong and didn't exist before. So now we come to this notion of, which will play a very important role, that a differential scheme X is simple with respect to some pseudo-functor P if pi 0, the categorical scheme of leaves, exists and is universal with respect to this family P. This implies that when you look at the corresponding morphism of precategories from precategory X to the discrete precategory on pi 0, that this morphism is of precategorical descent. In other words, the pullback of actions induced by eta is fully faithful. I could denote this functor as eta pullback, but in the context of differential schemes, I'd prefer to denote it as Cx. So simplicity guarantees that this functor is fully faithful. This would be important. Now we are able to formulate the indexed framework for differential Galois theory. We take the category A to be the full subcategory of differential schemes consisting of those differential schemes that actually admit pi 0. So not all of them do, but we just take those that do. Hence, we obtain a functor pi 0 into schemes denoted by X. And we have we choose some index data for descent, P, defined on schemes, which gives us, naturally, delta P, index data on differential schemes. And we also have, as we had on the previous slide, pseudonatural transformation C from P composed by 0 to delta P. And we can now sort of redefine what it means to be Picard-Vessiot for completely general morphisms of differential schemes. So a morphism of differential schemes in A is pre-Picard-Vessiot with respect to P, provided F is effective descent for delta P, and this we understand through our theory of differential descent, and X cross X, X cross X cross X must be simple for P. If we have a suitable forgetful functor from this descent data P into some class of scheme morphisms, so for example, if we have, say, if P is polarized quasi-projective morphisms, and U simply strips the polarization and returns just a quasi-projective morphism, then we're able to formulate a condition of being Picard-Vessiot with respect to U. The first condition is the same, and the second condition is that X is simple and that F is self-split. So remark, if f is Picard-Vessiot, this self-splitting implies simplicity of all the other relevant powers of x, so implies that f is pre-PV. And if f is pre-PV, then this kernel pair groupoid, GF, is an internal category in A, and when we attack it with the functor pi0, you get a precategory pi 0 of that in schemes, which we call the Galois precategory. In the slightly better scenario, when f is actually PV, then this Galois precategory actually becomes a groupoid. So the self-splitting condition gives you a category. So, okay, the template theorem for this general Galois theory is that if f is pre-PV, we have an equivalence of categories of objects split by f and Galois precategory actions in P. And if f is PV, then the right-hand side is slightly nicer because you get groupoid actions and not pre-category actions. A very rough sketch of proof is that when f is pre-PV, then all these objects are simple, but by the previous comment, the functors cx cross x, and cx cubed are then fully faithful, and that suffices to apply Janelidze's indexed Galois theory. One version of this is given in Borsuk-Janelidze book in section 6. Okay, so now we can apply this, we can specialize our choices for descent data for the family P and obtain different results. The theory we call quasi-projective theory, we still work over the base differential field of characteristic 0, and we take quasi-projective integral differential scheme over it, such that its only leaf is its generic point. And f is also assumed to be self-split. Those conditions then imply, so using our descent theory and everything, that f is Picard-Vessiot, that the Galois precategory is actually a group scheme over the base field, and we have a correspondence between split quasi-projective FPQC quotients of x over y and all closed subgroups of G. So this is now a full correspondence, and somehow the important bit is that this unifies both the linear Picard-Vessiot theory of before and strongly normal theory of Kolchin, which was somehow on the wish list of people to be treated using categorical Galois theory, but they couldn't figure out how. Even, say, Jerry Kovacic, who was famous in differential algebra, desired this as an objective, and Janelidze also, in his paper, outlines this as a very desirable project to do. So now it's kind of falls out of the template theorem. And so now something completely new, which allows us to work not only over a base field, but a base scheme, polarized quasi-projective theory, where for the index data P, we take polarized quasi-projective morphisms. And now a morphism of differential schemes is assumed to be such that X is simple. The underlying scheme morphisms is FPQC, and you have the self-splitting condition. These then entail that F is PV, that the Galois precategory is a groupoid, and we have an equivalence between polarized quasi-projective split differential morphisms and actions of this Galois groupoid. on polarized schemes. Right, so this is a pictorial display of somehow by how much we are able to generalize. So previously you could only work over a base field, which geometrically is just a point. I drew this point upstairs, I drew it a bit thicker. It's not just because those are maybe function fields of some varieties. So people did consider differential varieties, but then they could only work with their function fields, not precisely. And this would be the picture of examples that we can treat, which are, schemes endowed with vector fields. And if you ask about future directions, well, this work shows that differential Galois theory breaks into two conceptual components, and the first one is some kind of precategorical descent, and the second is categorical Galois theory. And you can basically apply the same principle to any situation where you have such two components. For example, we can immediately do the difference Picard-Vessiot theory, which also exists and is well established, but slightly less known than differential. This would be more Topos theoretic. Or you could work on, say, partial differential case, the case of Lie algebra of derivations, formal group actions, etc., etc. So that's it from me, and thank you very much for listening.